Hello and welcome to GCSE Revision. Today we're looking at GCSE Physics and specifically Radioactivity, which is P6 in the OCR Gateway textbook, and in this lesson we'll be looking at P6.1. To start off with some basic knowledge with atoms and isotopes. So protons, neutrons and electrons are all subatomic particles, and the reason they're called this are because they are within the atom, they are smaller than an atom. So we can see the protons, the neutrons, and the electrons. Here is a table with all the different details about these subatomic particles. So as we can see, protons and neutrons both are have a mass of 1. Electrons are 0.0005, but are counted as 0. So, neutrons. If an atom has a different number of neutrons to its element, they are known as isotopes. An example of an isotope is carbon-12. The 12 in carbon tells us how many subatomic particles there are in the nucleus, so how many protons and neutrons there are, and obviously there are 12 in carbon-12 because there are 6 protons and 6 neutrons. So how would you actually write an isotope out? So you'd have the mass number at the top and the atomic number at the bottom, which you should learn in chemistry. So for carbon-12 it would look like this, because you have 12 masses, because you have 12 different subatomic particles that weigh 1, and you have 6 protons, so that's a 6 plus 1 charge, 6 times plus 1, that is 6, and that's why the isotope of carbon-12 looks like this. So alpha, beta, and gamma. These are all 3 types of radiation. When a nucleus is unstable in an atom, it emits radiation. The radiation emitted can be made up of particles or waves, and the materials that emit radiation are known as radioactive. So, as I said, there are 3 types of radiation. There's alpha, beta, and gamma. And if we have a look in this table, we can see the different details for each type of radiation. Neutrons can also be emitted from a nucleus, we'll have a look at that later in the lesson, and also when neutrons are emitted they can decay into a proton and electron, hence in beta the particle of the beta is a fast moving electron. But how do you detect radiation? So the most common way to measure radiation is the Geiger-Müller tube. Essentially, it clicks when radiation enters it, and each tiny click is a current produced when the radiation ionizes one of the atoms of the gas inside of the tube. So, alpha, beta, and gamma have different penetrating powers, which means they can penetrate through different types of materials. And as we can see here, alpha gets stopped at a hand, or normally, more usually, a few sheets of paper. Beta is stopped at aluminium, and gamma, most of it, is stopped at lead. Not all of it, that's important. The radiation that is emitted by a radioactive material is known as ionizing radiation, and radiation can remove electrons from atoms to produce positively charged ions. So, alpha decay. If there is a very big nucleus containing high numbers of protons and neutrons, it would want to get rid of some of them so it could become stable. So 2 protons and 2 neutrons would join up to form an alpha particle, also known as a helium nucleus, and this would then be emitted from the nucleus of the atom. In beta decay, a neutron decays into a proton and an electron, and the electron is emitted as a beta particle. The proton is kept, and hence, as you can see in the equation, that is why the atomic number increases by 1, because there is a proton. And then the mass number stays the same, because although a neutron has been gotten rid of, the proton has come, and they both weigh the same, so therefore the mass number would stay the same. And finally, gamma decay. Gamma rays are electromagnetic waves, so they have no mass or charge, so when a nucleus emits a gamma ray, usually along a beta or alpha decay, the atomic and the mass number stay the same. So, neutron emission, as we spoke about earlier on. When some nuclei decay, they produce nuclei with large numbers of neutrons, and therefore the nuclei would just want to emit the neutrons to become more stable, as we can see in this equation. The charge on the nucleus wouldn't change, so the element would stay the same, but the nucleus is now more stable because it has gotten rid of that one neutron. Now, half-lives. Activity is the amount of radiation emitted per second, which is measured in becquerels. 1 becquerel is 1 count per second on the Geiger-Müller tube. But what actually is a half-life? So the activity of a radioactive material will decrease with time, but the time it takes for half of the activity to decrease is called the material's half-life. So, radiation in and out of atoms. So if you think, in an atom, there are electrons and there is the nucleus. The electrons have a negative charge and the nucleus has a positive charge. So why do the electrons not just spiral into the nucleus due to the two forces attracting? Well, this is because of energy levels. If you have a look here, we can see the energy levels. Scientists have discovered recently that electrons can only occupy specific energy levels within an atom. Usually the electrons will be on the lowest possible energy level, therefore having the lowest distance from the nucleus. However, an electron can increase energy levels when a photon with exactly the right frequency will come and be absorbed by the electrons. This is known as exciting the electron, and we would say it is in an excited state. When light of all frequencies is passed through some hydrogen gas, some frequencies are absorbed. An absorption spectrum shows a set of frequencies of radiation absorbed by an atom when excited electrons move to higher energy levels. So as we know, photons can come in and excite electrons so they go to higher energy levels. But when a photon has enough energy, and it's the specific right energy, it can completely remove the electron from the atom, ionizing the atom, which is what occurs during radiation, because radiation is made up of photons. The emission spectrum shows a set of frequencies of radiation emitted by an atom when excited electrons move to lower energy levels. So after the electron has moved to a higher energy level from the photons, it can then return to its previous energy level, emitting the photon it just took in. So, thank you for watching this lesson. I hope you've learned something, and I'll see you all next time. Goodbye.